All right, so now we're going to look at some examples of manifolds which arise in the context of manifolds of probability distributions. Okay, so one example obviously are Gaussian distributions. So you know that if you have a probability density function of a Gaussian distribution, it's described by the following. So the probability at some point x, right? And that parametrically depends on the mean and the sort of standard deviation, right? And so this is given by 1 over square root of 2 pi sigma, the exponential of x minus mu squared divided by 2 sigma squared with a negative sign here, right? So mu is the mean, right? And sigma squared is the variance. Okay, so it's clear that you can parameterize the space of Gaussian distributions, right, by the mean and the variance, for example. So we can parameterize the space of Gaussian distributions by sort of the following coordinates. So if you just have mu and sigma, and then you just need that sigma is greater than 0. Right, so this is a two-dimensional manifold. That is equivalent, that is sort of diffeomorphic to the upper half plane. Say in R2. Okay, and there's the entire manifold in question is covered by this single coordinate chart here, right? So in particular, it's like if you have a coordinate, well, if you have an atlas, which is only one coordinate chart in that atlas, right? Then by definition, it's like it satisfies the compatibility condition. So you don't really have to worry about the compatibility condition, which we talked about earlier. And having said that, you know, it's like there are obviously other choices of coordinates you can pick, right? So there are other possible coordinate systems. Right. So in particular, you can consider the moments of a distribution. Okay. So M1 is the expectation of x, right, which is obviously just the mean. So that's equal to mu. And M2 is the expectation of x squared, right? That's going to be mu squared plus sigma squared. Okay, so where E denotes the expectation of a random variable. Okay. Then this alternative set of coordinates, it's like having to do with the moments, is again a coordinate system. It's like for this space of Gaussian distributions. It's a coordinate system. As well. Okay. So there's one other choice. It's like which we denote by theta. Okay. So I'm just going to leave the definition of the Gaussian here. So another possible coordinate system is the following. Okay, so theta is equal to mu divided by sigma squared, comma, minus 1 over 2 sigma squared. Okay, so this is referred to as natural parameters. And then this is going to be a sort of convenient coordinate system for studying Gaussian distributions. Okay, so this is a convenient sort of coordinate system for sort of studying properties of Gaussian distributions. All right. All right, so that's just one sort of fairly naive example, because the space of Gaussian distributions is fairly straightforward, right? I mean, it has a single coordinate chart. It's like there, which is necessary. It's like to cover the entire manifold. There are sort of several equivalent atlases. It's like which we've discussed here. But again, it's like you don't really have to worry. It's like in this stage, it's like of it's like the change of coordinates maps. It's like which are important. It's like when you're trying to define whether or not a manifold has some sort of regularity. All right. Yeah. So let me just stop here. For now, it's like, and then it's like we'll look at a few more examples. It's like of manifolds or probability distributions. Okay, so let me just stop here for now.